Hello students, we are going to start chapter number 1, relations and functions. This is video number 1, and we have done this chapter in class 11 also. So today we are going to do some new concepts of relations and functions. If you like the video, please do press the like button. Now I'll do the quick recap first of class 11. This is a Cartesian product. If A is equal to 1, 2, B is equal to 3, 4, then the Cartesian product is written as A cross B. Will be the first element, there will be the ordered pairs. First element should belong to A and second element should belong to B, all those elements. So 1, 3, 1, 4, 2, 3 and 2, 4. Not 2, yes, 2, 3 and 2, 4 are the elements of A cross B. So this is the Cartesian product that it consists of all those ordered pairs whose first element should belong to the first set and second element should belong to the second set. So now we will define what is the relation. A relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian product A cross B. So if this is the set, so any subset of A cross B will be the relation. It can be a singleton 1, 3. 1, 3 will be one element, considered as one element, or it can be two elements, 1, 3, 1, 4. It's also a subset. Null set is also a subset of A cross B. That is also a relation. Universal, also you can see all the sets which contains all the elements is called the universal relation. So that is also the subset of A cross B. So any subset of A cross B will be the relation. So I have used arrow diagrams over here. Just see, this is the set A and set B under the relation R. If this is the set A, B, C and this is 1, 2, 3, so under the relation R, A is the ordered pair with 1, so A, 1, B, 3 and C, 2. This is indeed the Cartesian product of A cross B. What will be A cross B here? A1, A2, A3, B1, B2, B3, B, 3, C1, C2 and C3. This is the Cartesian product of A cross B, and A1, B3 and C2 are certainly the subset of that, therefore it is a relation. The domain is ABC and range is 1, 2, 3 and codomain is also 1, 2, 3 here. What is the difference between range and codomain? Codomain consists of all the elements of set B, but range will consist of only those elements which are associated with any element of A. So here all the elements are associated with the elements of A, so range and codomain are equal. Just see in this case, again under R, A and B are two sets. Domain over here will be ABC and range will be 1, 2 because only 1 and 2 are associated with the elements of A and 3 is not unused over here. So the codomain will be 1, 2, 3 but range will be 1, 2. So here domain, range and codomain are not equal. So let us see what is a function. Function is always a relation. It will be derived from relations only, but there is a condition on relation. A relation f from a set A to set B is said to be a function if every element of A, set A, has unique image in set B. So using arrow diagram, I can say if f is a function from x to y, so just see, this is f and there are two sets x and y. Is it a function? You can see that you can write like this: f of x is equal to 1, f of y is equal to 3, f of z is equal to 2. So all the elements are having a unique image, and domain over here will be x, y, z. Range will be 1, 2, 3 because only 3 elements are associated with the elements of x. And 4 is unused, so it will come in codomain. So codomain will be 1, 2, 3. For all the elements of set Y will be the codomain. Range will be only 1, 2, 3. Now let us see whether this is a function or not. From x to y, if I see, f of x is 1, f of x is also 2. So x is the element which is not having a unique image. F of x is 1, f of x is 2. So this is not a function. Now function definition says that it should have a unique image. Therefore element x do not have a unique image under f, so it's not a function. Now let us see the other example here. Here again x and y are two sets. This is the domain, this is the codomain. F of minus 1 is 1, f of 1 is 1, f of 2 is 4, f of minus 2 is 4. This is a function of x under f, as each element has a unique image. You can see that f of minus 1 is 1, f of 1 is 1, f of minus 1 is not 2, you can say that. F of minus 1 is not any other element. Minus 1 has got a unique image, 1 has got a unique image. F of 2 is 4, f of minus 2 is 4. So this is a function. So domain will be all the elements here in set X. Range will be the elements which are associated with the elements of X. So 1 and 4 will be the range, and codomain will be 1, 4 and 9. So now in this chapter we will learn about types of relations, types of functions, composition of functions and invertible functions. So today I am going to discuss types of relations. So let us see how many types of relations are there. Types of relation, first we will see identity relation. A relation R in a set A. When I write in a set A, that means it is from A to A. Okay, earlier I was considering two sets, A to B, X to Y, but now in set A means A to A. The relation in set A means R is from A to A. That means I will take the Cartesian product of A cross A. Is called empty relation if no element of A is related to any element of A. So all the elements of A should not be related to each other. Then that means the relation should have no elements. It should be a null set, and null set is a subset of A cross A. Null set is a subset of every set in fact. So for example, just see the example. If A is 1, 2, 3, 4, I always have to define a relation on a set. So this set I am defining on this set. So R is from A to A is defined as R is the ordered pair A comma B such that A minus B is equal to 10. And AB belongs to A. So A and B should belong to A because it is from A to A. Next set, the other set is also A. You can write here again if you want, for your understanding. 1, 2, 3, 4. So it will. So let us see the difference between 1 minus 1. 1, 1 will be one element. 1, 2 will be one element of the A cross A. 1, 3, 1, 4, 2, 2, 1, 2, 2, 2, 3. 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. These are all the elements of A cross A. So does any pair have the difference as 10? 1, 1, 1 minus 1. Is it 10? No, it is 0. 2 minus 1 is 1. 2 minus 3 minus 1 is also 2. And 4 minus 1 is 3. 4 minus 4 is 0. So there exists no element where the difference is 10. It can be negative. You can say 3 minus 4 is minus 1. But there is no element whose difference is 10. So there exists no element in A such that A minus B is equal to 10. So in this relation, so AB belongs to, for all AB belonging to A. So A is belonging to this set and B is belonging to this set. You can say that. So therefore it is an identity relation. So because there is no such element which is related in this set, if I define the relation like this. So we have to define a relation on our own, or it is given to us and we have to see whether it is identity or not, or we have to give an example on our own. Now just see universal relation. A relation R in a set A is called a universal relation if each element of A is related to every element of A. That means R is the whole set A cross A. Again it is a relation in set A. That means it is from A to A. And we have to consider the set A cross A. I am giving you an example. If I have A is equal to 1, 2 and R is such that from A to A, R is equal to AB, all those ordered pairs whose product is less than 5. The elements whose product is less than 5. So you can see that A cross A is 1, 1, 1, 2. You can write A again if you want, and then 1, 2, 1, 2, 2. Only these elements, and the products of all these elements is less than 5. You can see 1, 1, 1 into 1 is less than 5, 1 into 2 is less than 5, 2 into 1 is less than 5, 2 into 2 is less than 5. It contains the ordered pair, so it satisfies, this set property is satisfied by all the ordered pairs of R. So all the ordered pairs of A cross A will be included in R. So R is equal to A cross A. Over here it should be A, not B. It is in relation in A. So A cross A. Therefore, it is a universal relation. Next is these relations. There is a note over here. Identity relation and universal relations are also called trivial relations. So they are also called trivial relations. Now let us see reflexive relation. A relation R in set A is called reflexive if A belongs to R for all A belonging to, this is a sign for all A belonging to A. So A belongs to R can also be written as A R A. A is related to A. This is also, it can be written like this also. I'll give you the common example for all the whatever types we are discussing now. This is the common example. We will consider a set T, which is the set of all triangles in the plane. All triangles, T contains all the triangles. So it will contain all types of isosceles, similar triangles, congruent triangles, all types of triangles which are there, equilateral triangles, all kinds. But R is the relation in T. R is from T to T. A to A or T to T, that is how we take it in relation, such that R is equal to, in reflexive relation, T1 comma T2. T1 is congruent to T2. All those triangles from this set T we will take out, those who are which are congruent triangles. Which are congruent triangles, that the relation will include only those triangles. So now let T1 belongs to T. There is one element T1, only T1. We have to see only one element. And as every triangle is congruent to itself, so T1 is congruent to T1. So this is the relation. This is definition of a relation. When is it related? When the triangle is congruent to triangle 2. So T1 is congruent to triangle 1. So T1 is related to T1. That means its mirror image exists. So T1 belongs to R, or you can also write it as, or T1 is related to T1. So therefore R is reflexive. I will also show you a relation where R is not reflexive in the next example. First I'll do symmetric relation. After that I'll take an example to show that a non-reflexive and non-symmetric relation. Let us see first this. What is a symmetric relation? A relation R in set A is called symmetric if A1, A2 belongs to R, implies A2, A1 also belongs to R. That means the reverse, symmetry should exist. A1, A2 belongs to R, this is given to us, and then A2, A1 should also belong to R. If this is satisfied, then this should also be satisfied. Let us see in the above example, triangle example, if I take two elements, because I have to take two elements as given, that T1, T2 belongs to T, such that T1 and T2 belongs to R. That means they are congruent triangles. If T1, T2 belongs to R, so R will contain only those triangles which are congruent. So T1 is congruent to T2. Then T2 is also congruent to T1. We can write it in the reverse order also. It will not change anything. So T1 belongs to R. So this is a symmetric relation. This is R is symmetric here. Now I will give you an example of a non-symmetric relation, and this is also non-reflexive. Let A is equal to 1, 2 and R is from A to A, such that I am defining A comma B. A is less than, this is the property I have, this is the relation, A is less than B. So by this I will be determining the relation on set A. That means my first element should be less than the second element. So R will contain, because if I take it on A, so it will contain how many elements? The A cross A will contain 1, 1, 1, 2, 2, 1, 2, 2, isn't it? So, but only in one case, 1, 1, 1, 2, 1 is less than 2. So, 1, 2 belongs to R. So, but does 2, 1 belongs to R? No, 2, because 2 is not less than 1. So, 2, 1 does not belong to R, as 2 is not less than 1. Therefore, R is not symmetric. Here you can see that R is not reflexive also, because no element is less than itself. Like if I take 1, 1, 1, 1 is 1 less than 1? No. It is, if it is less than equal to, then I could have told yes, 1, 1 belongs here. But if it is only A less than B, so 1, 1, 2, 2 does not belong to R. So it is not reflexive also. Let us see transitive. A relation R in set A is called transitive relation if A1, A2 belongs, this is given. A1, A2, this property should be satisfied. A1, A2 belongs to R, A2, A3 belongs to R, implies A1, A3. That means this element and this element. The common element will disappear. So A1, A3 belongs to R for all A1, A2, A3 belonging to A. So this property is, if it is satisfied, then the relation is transitive. Now in this case, in the above triangle example, you can see T1, let T1, T2, T3 belongs to T such that T1, T2 belongs to R and T2, T3 belongs to R. This is the condition which has to be given in the transitive relation. So if this condition is satisfied, then T1 is congruent to T2, R means that only, and T2 is congruent to T3. So from here we can conclude that T1 is also congruent to T3 because they are congruent to the common triangle T2. So T1, T3 belongs to R and R is transitive. Now I am giving you an example of non-transitive relation also. If we have this element 1, 2, 3, this set A containing the elements 1, 2, 3 till 14, and I have defined a relation on A such that R consists of all those ordered pairs such that 3x minus y is 0 and xy should belong to A. Now just see here 3x, if I take x as 1, so 3 into 1 3 and y should be 3, then only this will be satisfied. So 1 comma 3 will satisfy. If I take x as 2, so 3 2s are 6 minus y should become 6, so 2 6 satisfies. If I take x as 3, so 3 3s are 9, so y should be 9, 9 also belongs here. So 3 9 is another, then 3 4s are x is 4, 3 4s are 12 and y has to be 12 which also belongs here. So 4 comma 12. If I take 5, then it will become 3 5s are 15 and y should be 15, but 15 is not here. So we will leave the rest of the elements. So now you can see here 1 3 belongs to R. Here 1 3 belongs to R, 3 9 belongs to R. The condition is satisfied of the transitive condition, first condition, but the next condition, what it should imply, 1 3 belongs to R, 3 9 belongs to R, then 1 comma 9 should belong to R, but it is not here. Is 1 comma 9 here? No. So 1 comma 9 does not belong to R, therefore R is not transitive. You can also see that this relation is neither reflexive nor symmetric nor transitive. So you can verify this on your own. So the last thing which you should know is the relation which is reflexive, symmetric and transitive. All of them is called an equivalence relation. So the questions will come, verify whether the so and so relation is an equivalence relation on a particular set. So this I will be discussing in the next class. Here the example which I took of the triangles is an equivalence relation because it is reflexive, symmetric and transitive. Thank you so much, students.